Greetings and welcome back. Today we'll be looking at the stability of ions. So this is incredibly important for reactions going forward. Reactions are what we will cover over the course of the next semester and a half in organic chemistry. In general, reactions are operations or transitions in which a molecule A turns into a molecule B. Generally, these things happen because of electrons moving around, which is something that we saw previously. But the way that you can tell whether or not a reaction would go forward, how much it likes to go forward, why it would happen in a certain way, or why it would happen to a certain part of a molecule but not to another part, often has to do with how stable the ion that you start with or the ion that you'll get afterwards. So understanding the stability of ions is crucial towards understanding reactions, which is all that we'll be doing for the next semester and a half. So buckle in and let's jump right in. Understanding and being able to predict which ions are more stable really boils down to four factors. One is within a row, the electronegativity. The second is a size within a column. The third is what's near those ions or neighbors. And the fourth is resonance. So we'll go through those one at a time, and that's what we'll be doing today. So the first trend when we're comparing ions is to look at electronegativity. And electronegativity is most important to consider within a column. Electronegativity, I think I spelled that right. So this is within a row of the periodic table. So anytime you are comparing things within a row, so for instance we have carbon, and then nitrogen, and then oxygen, and then fluorine, electronegativity is the most important thing to consider. So if we look at anions, which are minus charges, we can consider C minus versus N minus versus O minus versus F minus. Right, so within that row, those are our four main characters. Well, a minus charge would be more stable on a more electronegative atom because electronegative atoms like to have extra electrons, and a minus charge means you have extra electrons. So therefore, F minus would be the more stable anion, and C minus would be the less stable anion. Hopefully that's pretty straightforward. If you forget which way this goes, it's always worth looking at the periodic table and locating table salt. So Na is far to the left, it's a plus charge, it doesn't like to be minus. Cl is far to the right, it likes to be minus, it doesn't like to be plus. So the minus charges are more stable on the right, and in general, the positive charges are more stable on the left. So that being said, let's jump into the plus charges. So once again, we'll use our same main organic characters, oxygen, nitrogen, fluorine. And I'm not going to put C plus in here for a minute. I'll ask you a question about that in a second. But when we compare these guys, an N plus versus an O plus versus an F plus, the fluorine is still more electronegative, so it really likes to have extra electrons. Therefore, it really doesn't like to have electrons stolen away from it. So the F plus would be the less stable cation or plus charge, and the N plus would be by far the more stable plus charge. All right, and so that's the trend for electronegativity. It's pretty straightforward, but we only really use this when we're comparing things within a row. So what about when we're comparing things within a column? So the second trend is with size. So they get generally bigger when they move down the periodic table. And we use this when we're comparing within a column in the periodic table. All right, so in general, what we see is that if you look at the halogens, we could compare F minus versus Cl minus versus Br minus versus I minus. So those are our main halogens that we use. So when you compare these guys, it turns out that larger things, which have more electrons and more protons, and the outer shell is further from the nucleus, adding an extra electron in doesn't make a very big difference. For fluorine, you're going from 9 electrons to 10 electrons, which is a pretty big change. But for iodine, it's just one more on a huge pile, and so it really doesn't matter. So having that extra electron for iodine isn't a very big deal. So when we're directly comparing these guys, the most stable one is the largest one, or the further down in the periodic table. So this guy would be a more stable minus charge compared to fluoride, which would be a less stable minus charge. The same logic applies when we're looking at cations. We very seldom will see halogen cations, but the trend remains the same. When you're comparing F plus, and I'm just going to ... all this all the way down to I plus, well, for fluorine, it's a really big deal to take away an electron. Sorry, those should be 2 bonds. So for an F plus, removing that electron is a huge deal, and it's incredibly unstable. I plus, though, again, it has a whole pile of electrons around it. They're pretty far from the nucleus, and taking one away isn't that big of a deal. So what we see is that the trends here are the exact same. It's a more stable ion with a larger atom going down in the periodic table, so when you're comparing within a column. And F plus, which is much smaller, would be by far a less stable plus charge. And so it's interesting that electronegativity goes in opposite directions. We have more stable plus charges on the left side of the periodic table, more stable minus charges on the right side of the periodic table. But within a column, it just always gets to be a more stable ion when you go down, because bigger is better for plus, bigger is better for minus. All right, so those are the two first trends that we're looking at. Those are arguably the most important ones. So when you're comparing one ion versus another ion, these are the ones that you want to be able to use. When you're comparing an O plus versus a different O plus, or a C minus versus another C minus, that's where we have to get into trends 3 and 4, which we'll jump into right now. All right, so the third trend has to do with the neighboring atoms. So I'm going to give you a couple examples and then we'll talk about why. So let's compare a C plus that has 3 hydrogens attached versus a C plus that has 1 hydrogen and 2 carbons attached. So what a C plus means, what any plus means, is that the atom doesn't have enough electrons. So therefore, if you don't have enough electrons, what you'd like to have nearby is something that's willing to donate electrons to you. And carbons are inductively, that is to say through their bonds, electron donating. So carbons nearby are always willing to share electrons with their neighbors. Hydrogens nearby basically don't have any extra electrons to share because they're all being shared with that carbon already. So if you consider these two possibilities, a carbocation with no carbon neighbors and a carbocation with 2 carbon neighbors, this carbocation has 2 friends that are willing to share electrons with it. Therefore, its deficiency is not so bad. So if you have a plus charge, you want things nearby that will give you electrons. You don't want things nearby that will take electrons away. And that's the trend for when it comes to neighbors for any cation or anion. So to rank these, a lot of times we would say that this is your methyl cation, and C pluses are something we'll deal with relatively often. And then, based on the number of carbons next door, we use the terminology of primary, secondary, tertiary, or sometimes quaternary, but that doesn't apply to C pluses. So this would be a primary carbocation, meaning that it has 1 carbon neighbor to donate electrons to it. The secondary carbocation, which is this one right here, it has 2 carbon neighbors, and then it's also possible to have a tertiary carbocation, which is simply a C plus with 3 arc groups attached. R's just mean carbons. It could be methyls, it could be ethyls, just any carbons. And so when we're ranking these in terms of stability, of course, the tertiary one that has more carbon neighbors sharing electrons with it would be the most stable for a carbocation. And in this case, unlike our previous slide, we're comparing carbocations to other carbocations. And so when you're trying to compare like an O- versus a different O-, the first thing you want to consider is kind of what's around those guys. And so this would be the less stable C+. So to give you a kind of an idea, we'll never ever see this methyl carbocation. We'll very, very rarely see a primary carbocation, but a tertiary carbocation pops up quite a bit. And that's just because this is more stable, and therefore it exists. This is so unstable that it effectively never exists. All right, so let's look at some anions. We'll do the same thing. We'll consider a C-. So a C- with 3 H's nearby versus, let's say, we'll go all the way to the end and do a C- with 3 R groups. So once again, neighboring carbons will donate electrons. So whether or not it wants it, these neighboring carbons are sharing electrons with that carbon in the center. Well, the problem with the C- is that that carbon has too many electrons. So in the case of this tertiary carbanion, which is a carbon that has a minus charge and also 3 carbon neighbors, it has too many electrons, and furthermore, its friends don't know when to quit, so they keep sharing electrons with it as well. And that is really unstable. It already has too many, and furthermore, its neighbors are forcing more onto it. So therefore, this would be incredibly unstable. And so this would be a less stable minus charge. What would be nice would be if that carbon was next to something electronegative. So if that carbon, if a C- was next to, say, an O, that guy would inductively pull electrons away, which make it more stable. All right, so again with a C-, we can compare that methyl C- versus a primary C- versus a secondary C- versus a tertiary C-. And the one that is most stable is the one that has more hydrogen neighbors, which would mean that it has less carbon neighbors. So I'd prefer if you didn't try to memorize exactly primary versus secondary versus tertiary, but instead just look at that ion. Say, what is the ion? Minus means too many electrons, plus means not enough. If you don't have enough, you want more carbons nearby because they share electrons with you. If you are minus charged, that means you have too many, and therefore you don't want carbons, but you do want something like oxygens or something like that. All right, and then I will fill out the rest of this. This would be this would be a more stable C-. All right, so let's look at some relatively odd ones. There is a molecule that is lithium aluminum hydride. And I don't expect you to know about this yet, but this is an Al-, which is attached to 4 H's. The hydrogens don't really do anything, so that Al is stuck with the minus charge. It's not very stable the way that it is. There's another aluminum hydride that has 3 ethers attached to it, or O-tert butyls attached to it. Well, if you look at the periodic table, oxygen is far more electronegative than aluminum. So therefore, all of those oxygens would be pulling electrons away from aluminum. Aluminum with a minus charge is relatively unstable. However, in this case, it has too many electrons. The oxygens are pulling the electrons away. And because it had too many, this is a much more stable Al-. So this guy on the left would be comparatively less stable. This guy on the right would be comparatively more stable. And this can apply to anything, can apply to any ions, not just Al-, not just C-, not just C+. But you use the same logic for N pluses and O pluses and O minuses, etc., etc., etc. Our last trend is resonance. And this is the reason why we looked at resonance in the previous video, and it's all part of the same kind of general skill set, which is understanding ions. So resonance takes a little bit more work to understand, which is why we did that first. So resonance is all about spreading out an ion over a molecule instead of having it stuck in one place. So if we consider a carboxylate, which looks like this, it has resonance in which you can take the electrons away from the minus, that O has too many, make another double bond there, but that would give that central carbon 5 bonds, so therefore we need to also unshare some electrons and move them up to the O. That would give us a second resonance structure that would have an extra lone pair on the top oxygen, and therefore a minus charge, and then the one on the right would now be neutral. So this is a carboxylate, or the conjugate base of a carboxylic acid, and it has electrons spread over 2 oxygens. Effectively, each of those oxygens has an O with a half minus. If we compare that to the conjugate base of an alcohol, which would be an alkoxide, an O minus, this guy up at the top is far more stable, because spreading out a charge by resonance will always make something more stable relative to a charge that's stuck, like it is in the case down here, where you can't spread it out through resonance, it's just stuck where it is. So resonance will always make a charge more stable. It makes minuses more stable, it makes pluses more stable. Any way you can spread things out will make them more stable. So let's look at this for a carbocation. So with a C plus that has 3 carbons next door, we said that as you look at C pluses, this would be relatively pretty stable because it's got a plus charge, which means it doesn't have enough electrons, and you've got 3 neighboring carbons sharing electrons with it. So it's kind of overcoming its deficiency. They're inductively sharing electrons with it. There is no resonance that you can draw here. It's just that they're sharing electrons through those bonds. That's what we mean by inductively. So if we compare that to something like this molecule here. So in this case, we have a C plus. It's second, oh, excuse me, I made that one primary. Here, I'll put another CH3 over there. I'll put another CH3 over here. So this guy is a secondary carbocation, as opposed to this one, which was a tertiary carbocation. We consider that a secondary carbocation doesn't have as many carbon neighbors, but the one on the right over here has a resonance. That C plus doesn't have enough electrons, it also doesn't have enough bonds, so we can hop this double bond over like that. We can basically have that central carbon re-share it. And it gives us a resonance structure that would look like this. Now the carbocation is over on the right. So effectively that carbocation has been shared between 2 different secondary carbons. So energetically, these are a roughly equivalent energy. The one on the right has resonance and it has electrons shared between 2 secondary carbons. The one on the left doesn't have resonance, but the electrons are on a tertiary carbocation. So these 2 situations are of roughly equivalent energy. So that gives you a rough idea of how to compare kind of resonance versus neighbors. But in general, kind of to recap, when you have different atoms, so you're comparing a C minus versus, say, an N minus, that's where you want to consider whether they're within the same row or within the same column and use those trends. Electronegativity for within the same row and size within the same column. When you're comparing an O minus to a different O minus, you want to go to these 3rd and 4th trends. You want to compare resonance, if it exists, and you also want to look at their neighbors, if they're different. And rolling all 4 of these things together, you can get a lot of mileage out of this. These are really important to consider, and they're really important to study and know. And that's why this is the first essential outcome in the second half of this class. All right, thank you. Let's try a problem. Or maybe two. And thank you very much. I will see you in class. Please practice and bring your questions.